Imagine signing a blank check and handing it to a stranger. The moment they fill in the wrong amount, the check self-destructs. That's roughly what Bitcoin's SIGHASH flags let you do. A signature can lock the entire transaction, or just the parts you care about. To see why this matters, let's start with what a signature actually does in Bitcoin. Bitcoin uses two signature algorithms over elliptic curve key pairs, ECDSA the original and Schnorr, added with Taproot. Both run during script execution, typically through OP checksig, when the network verifies that whoever spends a coin holds the matching private key. The signature isn't just a stamp of approval, it's a cryptographic proof that the key holder authorized one specific message, a hash of selected transaction data. A valid signature gives three guarantees. Authorization, only someone with the private key could have produced it. Non-repudiation, the signer can later deny signing. The math ties them to it. Integrity, nobody can tamper with the signed message because changing even one bit invalidates the signature. These three properties are what make a signature meaningful. Without them, Bitcoin couldn't tell a legitimate spender from an attacker. Every transaction the network accepts rests on these guarantees holding for every input. The sign and verify operations are asymmetric. Signing requires two secret-aware inputs, the private key and the message hash. The sign function spits out a signature, typically a pair of numbers R and S. Verification is public. Anyone with the public key, the original message, and the signature can run the verify function and get back valid or invalid. No secret needed. That asymmetry is why Bitcoin works at all. The whole network can check your signature without ever seeing your key. Here's the key structural fact. Each input in a Bitcoin transaction is signed independently. A transaction with three inputs has three separate signatures, each produced by potentially different keys, each committing to its own message. That independence is the seed for everything that follows. Now, what message gets signed? It's called the commitment hash, a SHA-256 digest computed over a chosen subset of the transaction data, plus a single byte called the SIGHASH flag. The flag decides which parts of the transaction go into the hash. Change the flag and you change what the signature actually authorizes. So far, we've assumed a signature covers the whole transaction. That's a choice, not a requirement. There are three base SIGHASH flags. All hex value 001 commits to every input and every output. The default, what wallets use. None, 0802 commits to all inputs but no outputs. Outputs stay open. Single, 0N03 commits to all inputs but only the output at the same index as this input. Then there's a modifier. Anyone can pay. 0x80, bitwise OR with any base flag. It strips the input commitment down to just the signer's own input, leaving all other inputs open. Combine them and you get 6 total behaviors. Each one changes which fields of the transaction your signature pins down and which fields anyone else can still modify. Here's the procedure. Take the original transaction, copy it, then zero out or omit fields based on the SIGHASH flag. Append the flag byte itself to the serialized copy. Run SHA-256 to get the commitment hash. Sign that. The crucial detail. The SIGHASH byte is inside the hash. A miner or relayer can't swap your flag from auth to none because flipping the byte changes the hash, which invalidates your signature. The flag is self-authenticating. Whatever you signed, you signed. Nobody can rewrite the rules of your authorization after the fact. Use case 1, crowdfunding. An organizer publishes a transaction template with one fixed output, say 10 Bitcoin to a campaign address, and 0 inputs. Donors each add an input, signing with all or anyone can pay. Anyone can pay means each donor only commits to their own input. All means they commit to every output, which pins the destination. New donors can keep appending inputs without invalidating existing signatures. Once the input total covers the goal, the transaction is broadcast. One subtle weakness: the organizer could pad with their own throwaway input to inflate apparent funding, but the destination is locked, so funds can't be redirected. Use case 2, the dust collector. Dust means UTXOs so small they cost more in fees than they're worth. Sign a tiny UTXO with none or anyone can pay. That commits to your input but to no outputs at all. You're effectively saying, anyone can sweep this, send it wherever they want. A sweeper service collects thousands of these dust signatures, batches them into one transaction during a low-fee window, and adds an output paying themselves. The dust gets cleaned up. The sweeper takes the difference. Use case 3, the bearer check. A signer uses plain none, inputs locked, outputs completely open. On its own, that's dangerous. A miner could redirect the funds, but pair it with a co-signer on another input using SIGHASH all. That second signer pins the outputs in place. Now the non-signer has authorized spending their input, while the out-signer has fixed the destination. Together, the transaction is safe. This pattern shows up in multi-party protocols where one party authorizes funds and another determines where they flow. A clean separation of concerns. Most users never touch these flags. Wallets default to SIGHASH all, and that's correct 99% of the time. But the flexibility matters. Lightning Network and other Layer 2 protocols depend on this granularity to coordinate multi-party transactions safely. The next frontier is BP118, also called AnyPrevout, which lets a signature flow between different outputs. Critical for cleaner payment channel designs that don't need to pre-commit to specific UTXOs. The takeaway: a Bitcoin signature isn't a generic stamp of approval. It's a precise contract about exactly which bytes of which transaction the signer authorized. That precision is a quiet superpower of Bitcoin's design.